Professor, we can't hear you. Or I can't hear you.
Okay, let's see, maybe, yeah. Yeah, the exam was due today. If you're having trouble uploading it or there's some other issues, let me know. Let's see, can you guys hear me now? Okay, thanks. I want to finish up chapter 14 here and then just move on through 15, 16. So chapter 14, let's take a look at some of the other homework problems here. Here we're burning sulfur in air, and so it's the oxygen in air that's going to oxidize sulfur to form sulfur dioxide, which does have a foul, suffocating odor. You know, sulfur dioxide's toxic. And so you should do this in the hood if you're going to burn sulfur. You know, you shouldn't do it in the open air. Now, this type of problem, when we're going from gas to gas, is easy, as long as we're dealing with constant temperature and constant pressure. And so this will say constant temperature. Constant temperature means, it means this. Constant temperature, when you burn something, you usually generate a lot of heat and there's a flame, you know. And so the temperature is going to go up. What you do is, what it means by constant temperature is it doesn't mean the temperature stays constant for the entire duration of the reaction. What it means is you start off the room temperature, you burn it, and so it's going to get very hot. And eventually it's going to cool back down to room temperature. When it cools back down to room temperature, that's what we mean by constant temperature. Constant temperature just means initially you start off at room temperature, and when you take your final measurements, it's at room temperature. And so what's going to happen is the gas is going to expand at high temperature, but you know, as things cool back down to room temperature, it will contract, and that's where you're going to measure it. You're going to measure it at the same temperature. We could do it, you know, at different temperatures and just see, you know, what happens. You know, at the hotter temperatures, how much gas is formed, you know, at the maximum temperature. We might be interested in the peak temperature, you know, and so we might be interested in how many liters of SO2 occur when the temperatures reach a maximum. But in this particular case, you know, the SO2 is going to be generated, and then it's going to contract at the lower temperature. And so that's what they mean by constant temperature here. And so the temperature is constant, 26 degrees C, and the pressure is constant. You know, normally when you have a flame, the pressure might increase. You know, as the gases expand, the pressures could increase. But we wait until the pressure comes back down. And so this is constant pressure. And so if the pressure and the temperature don't change, then a gas to gas conversion is easy, because we only need one conversion factor here. And so the way it would go is because it's Avogadro's. So we read this equation in different ways. This is the mole ratio. And the mole ratio is always true. And so mole ratio. The mole ratio is 1 to 1 to 1. Okay. Now, the mole ratio equals the volume ratio for gases at, you know, at constant, we'll just say constant T and P, temperature and pressure. So at constant temperature and pressure, it's equal to the volume ratio. So here, the first one's a solid, and so that's not a gas. And so here, we'll just say it's a 1 to 1 for the gases. So 1 gallon of oxygen is going to give us 1 gallon of SO2. You know, 1 liter of oxygen is going to give us 1 liter of SO2. It's a 1 to 1 ratio, which is equal to the pressure ratio. For gases. But if we're dealing with pressure ratio, then it's going to be under constant volume conditions. It'll be constant volume and temperature. And so this top one we call Avogadro's. The bottom one we call Dalton's. So for example, if we have 1 atmosphere of O2, we're going to produce 1 atmosphere of SO2. You know, if we have 2 atmospheres of O2, we'll produce 2 atmospheres of SO2. It's a 1-to-1 ratio in this case. And so, of course, sulfur is a solid, so we don't count that. It's just for gases. So it's a 1-to-1 pressure ratio, or 1-to-1 volume ratio, or 1-to-1 mole ratio. Let's see, is the ideal gas law. When we look at the ideal gas law, you know, the volume is equal to nRT over P. If the temperature and the pressure are constant, then and the R is constant, these are all constants here. The only variable is N, number of moles. Same thing, pressure is equal to nRT over V. If the volume is constant and the temperature is constant, then we combine that with R, which is also constant, and the pressure is directly proportional to N. These can't be simultaneously true, you know, because we're either going to have constant pressure or constant volume. We can't have both at the same time. Although it could be simultaneously true. In this case, it is simultaneously true by coincidence. You know, it's not normally simultaneously true. It's just simultaneously true in this particular instance because it's 1-to-1 ratio, I think. Well, actually, I shouldn't even say that. There's only 1 mole of gas going to 1 mole of gas, so it's just because in this particular circumstance. So it's 35.2 liters of SO2 that were formed. And so how much O2? Well, it's a 1-to-1 mole ratio. And so therefore it's a 1-to-1 volume ratio. Therefore it's a 1-to-1 pressure ratio. And so it's going to be 1 liter of O2. We can pick any volume unit, liters, gallons, milliliters, whatever, for every 1 liter of SO2. And then this, you know, the T and P has to be restricted, T and P constant. Then this works. So it's 35.2 liters of O2. That's what we'll need. And so that makes stoichiometry quite a bit easier, you know, if we could just use those. And so we'll just use a volume ratio here. Now, the volume ratio works only when the temperature and pressure don't change, but from going from reactants to products. But if the temperature changes or the pressure changes or the volume changes and going from reactant to products, then we have to worry. The volume is going to change here. This is how we maintain constant pressure, because the way we maintain constant pressure is the volume has to expand and contract. It expands if you make more gas. It contracts if you consume gas. You know, and so the way we can maintain it is by letting the volume expand and contract. In this case, the volume doesn't need to expand or contract because we form the same amount. That's for Avogadro's. For Dalton's, we have constant volume. And so if you form more gas in a constant volume container, the pressure is going to increase. If you consume gas in a constant volume container, then the pressure is going to decrease. Here now, B, what if only the SO2 is at those conditions? So the SO2 is measured at these conditions. However, the O2 is measured at different conditions. O2 was measured at 17 degrees C and 847 torr. Now we can't use this, you know, because the pressure and the temperature are definitely going to impact the volume. You know, the higher the temperature, the greater the volume. The higher the pressure, the smaller the volume. And so those are things that are going to impact it. So the temperature has actually gone down. So temperature goes down, we expect a smaller volume. The pressure's gone up, so we expect a smaller volume. So this is going to be a smaller volume. It's going to be less than 35.2 liters, even though the amount of gas hasn't changed at all. The amount of gas is the same. It's just at lower temperature and higher pressure. And so what we have to do is we have to do stoichiometry. Now, this requires, if we do stoichiometry using I probably recommend using the molar volume method. We have to calculate 2 molar volumes. You know, the molar volume of gas under this pressure and temperature and molar volume of gas under this pressure and temperature. And so we'll have to calculate two, or we'll have to do two ideal gas law calculations. When we do two ideal gas law calculations, make sure, if you use ideal gas law, make sure that you label what moles you're talking about. You know, when you do an N calculation, a lot of people don't label what N is. Which N? Is it the SO2 or the O2? Makes a difference. And so people just don't label this and use the same N for O2. Well, in this case, they would have gotten lucky because of 1-to-1. But you have to label it SO2. So you could use ideal gas law, figure out what moles of SO2 are, and then do a mole-to-mole conversion, and then use the ideal gas law to figure out the volume of O2. What we'll do is we'll do a molar volume calculation for both of these. That's what I'll end up doing. Quick. And so I'm not going to do the ideal gas law calculation. We'll just use this method. The book uses that method as well. Calculate the molar volume. The molar volume is equal to RT over P. And so we'll calculate the molar volume under these conditions. R is 0.08206 liters times atmosphere divided by mole Kelvin times 700, actually temperature is 26 degrees C. 26 plus 273 is going to be 299 Kelvin. And so Kelvin cancels. Yeah. Divided by P, 741 torr. I just convert that into atmospheres. 1 atmosphere is 760 torr exactly. The torr cancels, atmospheres cancel, liters per mole is what we want. And so let's calculate the molar volume. Bring my calculator. Okay, it's going to be, what is it going to be? 0.08206 times 299 divided by 741. All right, I'm going to multiply by 760, just invert and multiply. 25.16. 25.16. I'm allowed 2 sig figs, but I'll carry 1 extra. Liters per mole. So it's a little bit higher than normal conditions. Under normal conditions, it's 24.5. This is a little bit higher volume because the temperature is 1 degree warmer, but the pressure is a bit lower, 741 torr versus 760 torr. And so this is the molar volume of the SO2. Let's look at the molar volume of the O2. The molar volume of the O2 is going to be different in this case here, as it's 17 degrees C. And so again, that's going to be 0.08206 liters times atmospheres divided by mole times Kelvin. 17 would be 290 Kelvin divided by 847 torr. And then convert that to atmospheres. So it's going to be 0.08206 times 290. We could use more sig figs in the Kelvin, you know, like 290.15 would be more sig figs, or 290.2. But usually most people just leave it at 3. So I've been doing the same. 21.35. Liters per mole. So mole of gas, you know, the volume it occupies is variable. This is why when you buy gases, you know, when I buy gases, I don't buy by volume, you know. because you can buy a lot of empty space almost. You usually buy gases by the grams, you know. So I buy a 2,000 gram cylinder of helium, you know, something like that. Then you know how much helium you're getting, no matter, you know, how it's packed in the tank. All right, so we have those molar volumes, then we can just do this using dimensional analysis. So we start off with 35.2 liters of O2, 35.2 liters of O2, and then convert that to moles using the molar volume. This works only for gases. We can't do the same for solids. You know, for solids, if we had the volume, we have to go from volume to grams using density. So volume to grams and then grams to moles using molar mass. And so for solids and liquids, we need the density. For gases, we only need the molar volume. We need the density and the molar mass. And so 35.2 liters, and then we know that 1 mole of gas under these conditions occupies 25.16 liters. Okay, so this is going to be under TP1. We'll just say TP1. All right, and then this is moles of O2, and so it's 1 mole of, oh, this is SO2, sorry, SO2. Then so it's 1 mole of O2 for every 1 mole of SO2. And so we'll get rid of moles of SO2 and convert that to moles of O2. And then for the O2, it's 21.35 liters per mole of gas under the temperature pressure conditions 2. So that should give it to us. Let's take a look. All right. They're using the combined gas law because I don't like this. I don't like this. Let me tell you why I don't like it. So what they're using is P1 V1 over T1 is equal to P2 V2 over T2. The reason, don't use this in stoichiometry. Because this one assumes N1 is equal to N2. In this case, N1 is equal to N2 because it's a 1-to-1 mole ratio. But what if it were, let's say, a 2-to-1 mole ratio? If it were a 2-to-1 mole ratio and you use this equation, it's wrong. You know, you'd have to use the combined gas law I gave you guys. And then you'd have to do a stoichiometry calculation to deal with it. You know, it would be P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And so the moles of gas changed in going from reactant to product. So you could use this one. It's possible to use this one, you know. But this is a stoichiometry problem. We don't do stoichiometry problems using a simple ratio like this. And then there's no stoichiometry here. You know, they didn't tell you that the moles, you know, N1 is equal to N2. Moles canceled out. And so this is not the correct way to do this. In other words, you could easily be tripped up. You know, you could easily be tripped up if, let's say it was 2 to 3 or 2 to 1 or 1 to 2 or whatever. Do it like we do stoichiometry. And so they should have made that, made it clear. The moles didn't change, the number of moles, but the identity of what it is did change. This is usually, you have a fixed quantity of gas, and the gas doesn't change, it doesn't undergo reaction. And so this is what they call the one-trick pony calculation, use old cliche. Gaseous chlorine dioxide is used to bleach wood pulp and in water treatment. Okay, so chlorine dioxide is a bleaching agent. What makes it a bleaching? Bleaching agents are good oxidizers, Chlorine's a great oxidizer, and chlorine in different oxidation states. Chlorine in the 0 oxidation state is a good one. Chlorine in the plus oxidation state. Chlorine in the negative oxidation state isn't a good bleaching agent. So for example, let's say you ran out of bleach, and would it be useful to dump in a whole bunch of table salt into your washing machine to bleach some clothes? No, because it's chlorine in the -1. It's already happy. It doesn't need any electrons. This should be a pretty good bleaching agent here. This gaseous chlorine dioxide, I expect to be a powerful bleaching agent. Why is that? Because the oxidation state of chlorine. I mean, chlorine's oxidation state here is +4. And so bleach wood pulp, probably for paper, and in water treatment. In water treatment, you can oxidize the bacteria and whatever else. It is produced by the reaction of chlorine with sodium chlorite. And so what's going on here with all this? Where's my pen? All right. So this is a redox reaction here. It's kind of a weird redox reaction here. Come on. Okay. This type of redox reaction is typically you just mix it and see what happens. So if you take chlorine, which is an oxidizer, and sodium chlorite, which is both an oxidizer, then it's the situation is it's both an oxidizer and reducer. So chlorine's both an oxidizer and a reducer. It could either gain or lose electrons. In this case, the chlorine, the Cl2, is going to be both. And which one is it going to be? Well, in sodium chlorite, what's the oxidation state there versus chlorine, and then we can see what happens with the changes in the oxidation states. So this is kind of an interesting reaction, but it's one of those ones you kind of mix and see what happens. It's hard to predict using the CHARP method, and for sure we wouldn't be able to predict it using single replacement. Sure. So this would be an example of a skeleton type redox reaction. You mix it, see what happens, you analyze the products, and then you try to balance everything out. How many liters of ClO2 measured at 0.961 atmospheres and 31 degrees C will be produced by 283 liters of Cl2 at 2.92 atmospheres and 21 degrees C? The Cargolici loves these kind of things. Normally chemists don't like to change the temperature and the pressure. Normally chemists like to have the same, what we do is we'll measure out the reactants, at room temperature and room pressure, and then we'll do the reaction, and then we'll wait for everything to calm back down to room temperature and room pressure, and then remeasure it, the products. Cargolici loves to change it. So the reactants are at one temperature and pressure, and the products are at some totally other random temperature and pressure. It makes no sense to do it this way. It's just more work, But anyway, we'll have to do this one the same way we did the last one. The last one we had to calculate the molar volume. Well, now we'll have to calculate the molar volume here. Higher temperature means bigger volume, and higher pressure means smaller volume. So I don't know which way that's going to go. And we'll have to calculate the molar volume here. This is much higher pressure, almost 3 atmospheres. And so the volume is going to be quite small, and the temperature is even lower, so the volume is going to be quite small. And so the 283 liters of chlorine were a very small volume, and this should be much larger volume, under these conditions here. But let's look at the reaction here. It's Cl2 and ClO2 gases, and so this is a 1-to-2 mole ratio. And so in this case, they aren't going to use this ridiculous equation they used here. This equation will not work in this reaction because it's a 1-to-2 mole ratio. Well, they still used it. What they're doing here is this. What they're doing here is, I see what they're doing now in this case. In this case, what they're doing is they're going to figure out if this chlorine were at this pressure versus 3 atmospheres. So what they're going to do is they're going to take the chlorine and reduce it from 3 atmospheres to about 1 atmosphere. And the volume should about triple here. But they're going to lower the temperature, so the volume should triple, and actually not, they're going to increase the temperature, so the volume is going to more than triple. And so what they're doing is they're figuring out the volume of the chlorine under these conditions here. Okay, once they figure out the volume of chlorine under these conditions, then they're just going to use a volume-to-volume conversion here, because the ClO2 will be in the exact same conditions 2 here. And so they're taking the chlorine, going to conditions 2, and then from there, they're doing this. I don't prefer that method. I mean, I guess it's fine. Now I see what they're doing here. I just prefer to just do it stoichiometrically. All stoichiometry problems I do the same way. You could do it whatever way you want. But this is the way I would have done it. I would have calculated the molar volume here under these conditions and calculate the molar volume here, and then just start off with this. So I don't know what's going on with my pen. Oh, I know what's going on with my pen. All right, let's calculate the molar volume here. Molar volume is RT over P. And so R is 0.08206. T is 21 degrees. So that's going to be 294. Okay, so times 294 Kelvin. Liters, atmosphere, mole, Kelvin. 294 Kelvin. Pressure is 292 atmospheres. .92. 8.26. Wow, that's really small. 8.26. Let's go with 8.262 liters per mole. So at high pressures, the volume gets compressed quite a bit. Okay, let's calculate the molar volume here. So the molar volume is equal to 0.08206 liters atmosphere per mole Kelvin. Temperature is going to be 2304 Kelvin divided by 0.961 atmospheres. .08206 times 304 divided by 0.961. 25.95. Okay, this is a little bit bigger than what we expect, lower pressure and higher temperature. Normal is 24.5 liters per mole. And so it's gone down quite a bit, or gotten a little bit bigger here. And so the way I do it is just the standard stoichiometry, 283 liters of chlorine. Then convert that straight to moles. 1 mole is 8.262 liters. This is PT, let's call it PT1, although it's product, or no, it's reactant. So we'll call it PT1 or PTR for the reactants. Let's call it PTR, reactants. Okay, now we'll do the mole to mole conversion here, and that is, there are 2 moles of ClO2 for every 1 mole of Cl2. Okay, and then we're going to use this 25.95 liters of gas per mole. This would be the products conditions here. And so what does it come out to? 2.8 or 283. 283 divided by 8.262 times 2 divided by, or times 25.95. We're allowed 3 sig figs. And so 1,777 liters of ClO2. Since we're allowed 2 sig figs, this is going to be 1,800 liters of ClO2, or 1.8 times 10 to the third liters ClO2. How many sig figs? 3 sig figs. Sorry, we're allowed 3 sig figs. 178. 178. I mean, not 178. 1,780. 1,780 liters. Or 1.78 times 10 to the third liters. So I would set up a standard stoichiometry problem. The reason is especially if you get into mixtures and stuff, it's complicated. Although this works here, I see what they're doing. They should label it. You know, this is the volume of chlorine under product conditions. This is the volume of chlorine under reactant conditions. So they're saying if we just change this, you know, the sun to the same conditions, we'll be okay. Okay, let's go on here. In the natural oxidation of hydrogen sulfide is also a poisonous gas here. So you're burning hydrogen sulfide. When we burn hydrogen sulfide, we're going to form oxides of sulfur and water. You know, when we burn hydrocarbons, we form CO2. Well, SO2 is a common gas that's formed. So SO2, although SO3 would be, you know, complete oxidation, because sulfur can go up to +6. You know, here in SO2, sulfur is at +4, but that's usually where it stops. And then it's possible to undergo further oxidation here in this combustion. Just goes to sulfur dioxide. How many milliliters of hydrogen sulfide measured at? Okay, so we want H2S. We'll be using the reaction that also uses 704 milliliters of O2. This is kind of weird because O2 and H2S are both reactants. And so normally when you react these together, you don't do them at totally different temperatures and pressures. If we're reacting the reactants, we do it at the same temperature and the same pressure. So this is a very weird problem. But anyway, it's the same kind of deal. What they're going to do is they're going to use the combined gas law to change the O2 into these conditions here. And so the O2 will be, maybe the O2 was measured at some other day, on some other day, but it still doesn't make sense. And so they're going to use the combined gas law. This is what I'm predicting. They're going to use the combined gas law to have the, to change the volume of O2 to these conditions, and then use a volume to volume conversion, just like the last problem. And that's what they do. So they convert the volume of O2. Geez, that is annoying. I don't know why it's doing that. And then then once they get the O2 under the same conditions as the H2S, then they can use the volume to volume conversion here. And so again, whichever way you like, you know, although calculating molar volumes is a hassle, I would just do it. And so here I would just go from milliliters to liters and then calculate the molar volume. Once I have the molar volume, I could go liters to moles, and the moles to moles, and then moles to liters using this new molar volume here. The reason I do it is because most problems aren't like this. Most problems you're going to be working under the same conditions, so we could do it volume to volume. The reason we need volume to volume works great for gases, but when you don't have gases, like for example, this is going to be a liquid. And so water is going to be a liquid under these conditions. And so there, you know, we got to use molar volume. So what we're going to do is if we're figuring out how much water, liquid water we have, we'll go from milliliters of O2 gas to liters of O2 gas, liters of O2 gas to moles of O2 gas, moles of O2 gas to moles of H2O liquid. And then we'd need the molar mass to go to grams of H2O liquid. And then we'd need the density to go to milliliters of H2O liquid. And so if I had asked you H2O liquid instead, this is not going to work, obviously, because H2O, well, not this. This will work, you know, but this will not work here. This will not work. And so doing it the standard stoichiometry way gives you more branches, you know, gives you more versatility and in the complexity of the types of problems that you can solve. You know, although this is one useful tool, it doesn't save that much time. But the problem is every single problem is going to be like this. This is, I don't like the chapter because it's kind of repetitive in that sense. There isn't enough variety for me. In fact, all these problems are the same, including the evens. Okay, so let's go on. Determine whether each of the following statements is true or false. The molar volume of gas at 1.06 atmospheres and 212 degrees C is less than 22.7. Okay, 22.7 is a number that they want you to memorize. 22.7 is, this is the molar volume of gas at 0 degrees C and 1 bar. And so like you now, I had to memorize it, but the one I memorized is 22.4. That was the molar volume of gas at 0 degrees C and 1 atmosphere. It's 22.4. This is the molar volume at 1 bar. So it's a little bit bigger than what I had to memorize because 1 bar is lower than 1 atmosphere, a little bit lower pressure. And so this is 1.06 atmospheres. So 1.06 atmospheres, a bar is about 1.01. There are 1.01 bars in an atmosphere. And so bar is like 0.9 something atmospheres. So this is a little higher pressure. So a little higher pressure, the volume should be less. That's correct. But when we look at the temperature, the temperature is 212 degrees C versus 0 degrees C. The temperature is much higher. And so the pressure is a little bit higher, but the temperature is a lot higher. You know, we're talking about Kelvin though. And so this will be 273. This would be like 400, almost 500 Kelvin. So we're going from about 300 to 500 Kelvin. And so that's much more significant, almost doubling. And so the higher temperature is going to be more. And so this is going to dominate, you know, and so this is false. The mass of 5 liters of ammonia is the same as the mass of 5 liters of carbon monoxide if both volumes are measured at the same temperature and pressure. No, they're going to have the same number of molecules. And so the number of molecules will be the same because the volumes are the same and the temperatures and pressures are the same. So the number of moles is the same. Therefore, the number of molecules is the same. However, a molecule of ammonia weighs different than a molecule of carbon monoxide. You know, how much does a molecule of ammonia weigh? Well, nitrogen is 1401, hydrogen is 101, so this is 1704 grams per mole. Carbon's 12, oxygen is 16, so this is going to be 2801 grams per mole, 28.01. And so carbon monoxide weighs a lot more, about double. Well, not quite double, but less than double. And so the answer is false. At a given temperature and pressure, the densities of two gases are proportional to their molar masses. Yes, that's true. If you go back to the, you know, the density equation, the density equation is equal to molar mass times P or RT, so it's true. To change liters of gas to moles, multiplied by RT over P. RT over P is the molar volume. And so molar volume will convert moles to liters. They're asking to change liters to moles, so we got to invert the molar volume. So this is false. It should be the molar volume inverted. Calculate the volume of 6.74 grams of, this is called ethene. You know, when we do the Lewis structure, there's certain patterns. In organic chemistry, you can learn some patterns here. In organic chemistry for hydrocarbons, we have CxH2x plus 2. If it's a 2x plus 2 hydrogens, then it's all single bonds, you know. If it's CxH2x, then there's got to be some double bonds in there, you know. If it's a CxH2x minus 2, then maybe there's some triple bonds in there. And so after you do organic chemistry, you can look at this and see, oh, there's got to be, you know. But we'll try it. You know, we're going to just try it using what we know here, not that. When we look at this, does this look good? No, there's something not quite right about it. And what's not quite right about it is carbon. Carbon only has 3 bonds. Carbon likes 4 bonds. So we'll just put a double bond there. Now it's good. So this is the Lewis structure of this. This is called ethene. Ethene. Calculate the volume of 6.74. This is trigonal planar. This is trigonal planar. You know, bond angles should be all about 120, except the double bond takes up more space. And so what happens is the 120-degree angles get distorted a little bit. And so the double bond takes up more space. This angle gets pushed out, and this angle gets compressed in, you know, a little bit. And so what happens is this one, you know, grows to about 122. This one goes to about 122 also. And this one shrinks. These have to add up to 360. So, you know, if these are 122 and 122, this one's got to shrink by 4 degrees. So it's going to be 116, roughly. Those will be the angles. But the ideal angle is 120 because it's trigonal planar. That would be the ideal angle for that. Now, you know, these are just guesstimates, the distortions here because of the double bonds. Double bonds take up, you know, there's going to be greater repulsions there. So they're going to take up more space, the double bonds. This is formic acid here. I made that there earlier. It's going to show something, but I forgot what I was going to show. Well, I was going to show that this is trigonal planar, and this is bent or angular. This is the lone pair. We don't see the lone pairs. The lone pairs here. One lone pair projecting out, one lone pair projecting in. It's bent like this, this angle. Let's see. Let's just take a look at ethene. So we'll use this carbon. This is also called sp2 carbon. sp2 carbon, you're going to talk about hybridization in Chem 1A. Unfortunately, they don't talk about hybridization in Chem 4. This is ethene. Do you see how it's totally planar? It's flat. You know, these yellow sticks are going to be attached to hydrogen. So we've got 4 hydrogens here. We call this ethene or ethylene. Ethylene is another name for this. I'm going to replace that. So we got that. You can check out the angles. So why do, you know, sometimes they just don't show the hydrogens to make things clearer. The hydrogens are there. They're just not showing it. Like if it went space filling, you can see the hydrogens in yellow here, which is unusual. Usually hydrogens are white. Those 2 carbons. Let's take a look at the angle. I measure the angle. We need 3 atoms to define an angle. So this is going to be HCC angle. It's 121.75. So you can see that the double bond distorts it. It should be 120, but it's closer to 122. This angle will be exactly the same. This HCC angle. 122, let's say. And then we'll look at the HCH angle. This is going to be compressed to about 116. You can see the angle down here. That's what we got for this. Let's take a look at some of the orbitals for these. It doesn't show us much. These are what we call molecular orbitals. They have these funny shapes. You know, we only looked at atomic orbitals, the S, the P, the D, but in quantum mechanics, the molecules also have orbitals. Yes, you can see them here. This is an orbital energy level diagram here in electron volts. Electron volts is a unit that's very popular with physicists. So we can convert it to electron volts. From joules. Joules are very popular with chemists. So calculate the volume of 6.74 grams of ethylene. So what we have to do here is this. We could do this stoichiometrically, or we could do this, you know, the different ways we could do this. One way we could do this is we could just go from grams to moles of gas. Once we have moles of gas, then we can use the ideal gas law. That's one way. Or we could do this using dimensional analysis and getting the molar volume here. And so, I don't know which way, you know, for this one, you might want to just go grams to moles and then use the ideal gas law. That would be the quickest. Using dimensional analysis in this problem is fine too. I'll do it dimensional analysis way. If you do the dimensional analysis way, then let's figure out the molar volume for this. Dimensional analysis might be a bit more work in this particular instance, but it's RT over P, 0.08206 liters atmosphere per mole Kelvin, times the temperature, 273, 273, 331, 4, 314. 314 Kelvin. Pressure 733 torr. All right, so we've got 0.08206 times 314 divided by 733. times 760. This is going to be 26.71 liters per mole. So it's a little bit bigger because of the temperature and lower pressure. Okay, and then we need the molar mass of ethylene or ethene. And so we got 2 carbons. It's 2402. We got 4 hydrogens. It's 404. And so 2806 molar mass. And so we'll just go 6.74 grams of C2H4. And then 1 mole of C2H4 weighs 28.06 grams. And then we don't do any mole to mole conversion because there's no, reaction here. And so we're just going to use the molar volume, 26.71 liters of gas per mole of gas under this pressure and temperature conditions. And so that's the way I do it here. I try to do things using dimensional analysis versus algebraic. They just actually, this is good too. I guess. I don't know. Where'd this equation come from? Well, this is rearranging the molar mass equation. I guess you could do that as well. I just don't like too many variations of too many equations. Too many things to remember. That's essentially we're just going to get the same answer. So I wouldn't even bother with this equation. 50, find the mass of 57.9 liters of krypton at 775 torr and 6 degrees Celsius. So this one I would do, using dimensional analysis again, Actually, dimensional analysis is a very powerful tool. And so again, I'd probably just get the molar volume here. I need the molar mass of krypton. I'd have to look that out. Krypton's a gas. And so figure out the molar volume here. Can do. Molar volume is going to be RT over P, so 0.08206. 0.08206 times temperature. 273 plus 6 is 279. 279 divided by the pressure, 775, and then convert it to atmospheres times 760. And so it's 22.45, 22.45. So it's a little less because the temperature is lower and the pressure is higher. 22.45 liters per mole. Yes. And so we go 57.9 liters of krypton gas. And then we know 1 mole of any gas occupies 22.45 liters under these temperature and pressure conditions. And then what is the molar mass of krypton? Let's see, you could ask Siri for that maybe. Or if you have your periodic table handy, that's probably a lot better. There we go. Krypton, you find, okay. Actually, I should just look up their answer. 83.70, 83.80, 83.80 grams per mole. Here I rounded it actually, it's 83.799, but for molar masses and atomic masses, we'll just round it to 2 decimal places. This is krypton per mole krypton. Let's see how they did it. All right, they used this equation, rearranged it, which is fine. If you like this equation, then go ahead, use that. I'd like to keep things simpler. And so this, for me, is pretty straightforward, dimensional analysis. What is the density of H2S? Now this one I would use the fancy equation for, because density and molar mass calculations, that's more useful. We don't need to use that equation, but it might be easier to use it. Or we could also do this using dimensional analysis as well. You know, density of that. How would we do this using dimensional analysis? Let me show you how I do this using dimensional analysis versus memorizing an equation. We're going to be given the molar mass of H2S, or we could just calculate it easily. And so if I were to use dimensional analysis, I have H2S, 2 hydrogens, that's 2O2. Sulfur is 3206. And so the molar mass of this is 3408. Now, sulfur varies depending on what periodic table you look at. It's 3206 in some and 3207 in others. We'll just go with this, 3206 for that. And so dimensional analysis, I'm going to start off with 34.08 grams per mole. Now, the grams here, right, is what we want for density. We want grams up in the numerator, but we don't want moles down here. We want liters down here, because density for gases is grams per liter. Density for solids and liquids is grams per milliliter, but gases are 1,000 times less dense, so grams per liter. And so we need to convert moles of gas, this is a gas, to liters of gas. Well, we can convert moles of gas to liters of gas using the molar volume here. And so let's go ahead and calculate the molar volume. The molar volume is going to be R. I'm not going to write out the equations just to save time, because 0.082606, I'm going too slow. 0.08206 times T, 14 and 273 would be 287, divided by P, 0.972 atmospheres. That's 24.22. Okay, so we have here 1 mole of gas is 24.22 liters of gas. And so moles cancel, and that gives us grams per liter. Well, grams per liter is what we want. And so let me flip this density over. And times 34.08. 1.40. We're allowed 3 sig figs here. 1.406 grams per liter. So it's denser than air, you know, because this weighs more than air. Air is about 29. The average molar mass of air is about 29 grams per mole. H2S is heavier, so it's going to be more dense. There, let's see what the book does. Your book is going to use this equation. We derived this equation in class, you know. Molar mass, P over RT. I don't like to memorize very many equations. Or, I mean, it's fine to derive it, though. If you can derive this equation, that's good. Or you can just use dimensional analysis. 52. Well, let's see. 83.8. Let me see. Talking about 83 point. Let's, this is the atomic mass of krypton. This is from the periodic table. I got it from. Oops. A lot of these periodic tables are just ads, so it's dangerous to go there sometimes. I had a good one. Why don't they have the masses in the Wikipedia periodic table? I don't know. DuPont. Let's try that. No, it's not good either. Well, this is interesting periodic table. Oh, this isn't an interesting periodic table. Forget it. I thought it was a PDF. pttable.com. I don't know why. You know, our book. Oops, I misspelled that. P-table. So I rounded it. You could see krypton there. $83.798. I rounded it to 83.80. Yeah, it's break time. So, okay, we're going to take a break here for 15 plus minutes. Okay, so let me pause the recording. Okay, we're going to get started again. I took a little longer break, but let's go back to the homework. At 17 degrees C and 0.835 atmospheres, 16.2 liters of ammonia has a mass of 9.68 grams. What is the molar volume of ammonia at those conditions? Well, if they're only asking us for molar volume, we just need the temperature and the pressure. So we ignore all this other stuff. Temperature and pressure, RT over P. RT over P. And so molar volume is good for any gas. It doesn't have to be ammonia. It could be any krypton, H2S. That's the thing about gases. This is a physical. Of course, the chemical properties of gases are going to be totally different. Ammonia is totally different than H2S, which is totally different than krypton. Chemical properties of the gases are different, but their physical characteristics in terms of pressure, volume, temperature, and moles are all the same. Their densities are different, though, so that's a physical characteristic that's different, but the other characteristics are the same. 53, a 7.60 gram sample of pure liquid is vaporized at 183 degrees C and 179 torr. At these conditions, it occupies 3.7887 liters. What is the molar mass of the substance? So there are two ways we can do this. We could try this. We could do this using the molar volume and dimensional analysis if we want, or we could use the equation, you know. The equation I derived earlier. The equation is that the molar mass is equal to, that could be a useful equation to know. So the molar mass is equal to the mass over N. And we know that N is equal to PV over RT. So it's the mass times or divided by PV over RT. So this is the mass times RT over PV. So if we know the mass, which we have here, we know the temperature, which we have here, we know the pressure, which we have here, and we know the volume, then we can just solve for the molar mass. Let's work out here. There's other ways we could solve this as well, you know. But this equation is pretty useful for gases. The other way we could solve this is by calculating the molar volume here, and using that to figure out how many moles we have, and then taking the grams divided by the moles. The gram to mole ratio is the molar mass. So we could do it using, we need the moles on the bottom, so the liters would have had to have been on the bottom. So we could go grams per liter, you know. But here they use the equation here, mass times RT over PV. This would have been a little bit tricky here for dimensional analysis, because where do we start in dimensional analysis here? Well, we know that liters, according to Avogadro's, is directly proportional to moles. And so this could have been a tricky start, because I probably would have started like this, 7.60 grams. So that's what we want on top. And then I would have went 3.87 liters on the bottom. And so we have this many grams per liter. Well, this is the density. And then I would use this to get the molar volume. Once I have the molar volume, then I know how many liters per mole I have. And then I'll just cancel out the liters. And then I get grams per mole. Well, that's what we want. And so from this, I would have gotten the molar volume and thrown it here using dimensional analysis. And that way I wouldn't even bother. Well, molar volume is kind of useful, so you need to know the equation for that. The density of nitrogen at 0.913 atmospheres and 18 degrees C is 1.07 grams per liter. Explain how this shows that the formula of nitrogen is N2 rather than just N. Well, the difference we could do, because we know molar mass of a gas is related to these characteristics as well. And so the molar masses of these are totally different. You know, if I had a mole of N2 that's going to weigh 28.02 grams. And so this is going to give me a molar mass of 28.02 grams per mole. So if I had a mole of particles, it's going to weigh 28.02. If I had a mole of these particles, it's going to weigh half as much, 1401 grams per mole. And so these will have totally different mole. Now the moles, you know, the gases don't care what the moles are, you know, it just cares how many there are. And so what we need to do is we need to figure out what the molar mass is here. And so we could use dimensional analysis for this. We have 1.07 grams per liter, and we just need to convert liters to moles. We need to convert liters to moles. Well, the molar volume will do that for a gas. And so we could calculate the molar volume here. Molar volume is going to be RT over P. And so R is 0.08206. T is 273, 280, 291. Divided by P, 0.913 atmospheres, 26.15. And then that gives us grams per mole. And so 1 times 1.07 gives us 27. This comes out to 27.98 grams per mole. And so it's closest to this. There's going to be some experimental error, it looks like. You know, it's not right on. So there's some experimental error here. But it's not half that. And so it's got to be N2, not N. So they calculated the molar mass. They rounded it to 3 sig figs, 28. We'd have to do the same. We're only allowed 3 sig figs here. Okay. At a given temperature and pressure, what mathematical relationship exists between the density and molar mass of a gas? Explain your answer. You know, they wanted an equation. So we could come up with an equation here, you know. The equation I did was this. If I use my equation is that the molar mass is equal to the density times the molar volume. This is the equation I just did for this, you know. But the molar volume is RT over P, and so it's density times RT over P is another equation, you know, we could do. And so the density is the molar mass, 1 over the molar volume, sorry. I did 1 over molar volume. Molar volume is liters per weight a minute, liters per mole. Oh yeah. I'm solving for molar mass here. Molar mass is density times RT over P. If I solve for density, then density is molar mass times P over RT. You know, P over RT would be 1 over the molar volume here. K, what are they calling K? K is some proportionality constant. They're calling K is proportionality constant. So density is equal to the molar mass divided by the molar volume, or molar mass times P over RT. Labels have become detached from cylinders of 2 gases, one of which is known to be propane, C3H8, and the other butane, C4H10. The name tells us, you know, the structure. Prop means 3 carbons. Ane means there are no double bonds. And so it's a chain of 3 carbons. And so propane is this 3 carbon hydrocarbon with no double bonds. Propane looks like this. Obviously this is zigzag, but you know, the Lewis structure, we don't have to write it zigzag. And so C3H8, it's 2, you see it's 2x plus 1, 2x plus 2, or 2n plus 2, you know. And so I knew this one is 2 times 4 is 8, plus 2 is 10. So this is just a 4 carbon chain. So just add 1 more carbon to the chain. This is butane. Propane is a borderline gas liquid, you know, it's right on the edge, you know. Butane is a liquid. As these get bigger and bigger, you know, pretty soon they'll become a solid. Like butane, pentane, hexane, they're all liquids. As these get smaller, they become gases like methane, etc. It has to do with intermolecular forces. The type of intermolecular force is the what we'll call the dispersion force, which we're going to look at, I think, in the next chapter. The densities of the 2 gases are compared at the same temperature and pressure. The density of gas A is 1.37 grams per liter. The density of gas B is higher. Okay, so this molecule weighs more. And so if it weighs more, it's going to have a higher density. So gas B is butane. Gas A has got to be propane. Okay, what is the density of gas B? Well, the different ways. We could do it by proportionality, you know. We can do it by proportionality. Let me just do one thing really quick. That is, we can get a proportionality of the masses here. That's one way. There are other ways we could do it. I could just use the equation to calculate it, but we'll do it by proportionality here. If A is 1.37, then how much heavier is B compared to A? And so we'll just do that way. There are different ways. The only difference is one CH2 group, you know, heavier. But we can do it the total mass. And so we got 3 carbons. 3 carbons is 3 times 12 is 3603. And then 8 hydrogens is 808. And that's 4408. Here we're going to have 4 carbons. So this is going to be 4804. And 10 hydrogens, which is going to be 1010. And so this is going to be 5814 grams per mole. And so what we have here is we just use dimensional analysis, 1.37 grams of butane per liter. And then all we're going to do is a gram to gram, you know, so we're going to say that we're going to have 58.14 grams of oh, actually this is propane. 58.14 grams of butane for every 44.08 grams of propane. And so the grams of propane cancel, and that leaves us with grams of butane. And so I would do 1.37 times 58.14 divided by 44.08 gives us 1.80. So butane is going to be obviously heavier, 1.806 grams per liter. See what they did. Well, they did the same thing. They got a proportionality. I did it for every mole, you know, for every mole. Or, you know, you would normalize it. They put in the moles here. The moles are going to cancel if they're the same number of moles, which they are in the liter. They're the same number of moles. And the organic chemist has produced, organic chemist works with hydrocarbons and those kind of things. Inorganic chemists work with the rest of the periodic table, you know, carbon-based compounds. Organic chemist has produced a solid that she believes is to be pure. You know, that's always tricky. You know, are you making a pure thing or do you have a mixture? You know, if you have a mixture, it's a bit of a headache because mixtures, you know, more variables associated with that. If it's pure, it's easier to deal with and easier to characterize. She expects a molar mass of 346 grams per mole. All right, using 4.08 grams of solid. Okay, this is one way she can check the purity of this. You know, if she did indeed make it a pure, then the molar mass should come out 346. If there's impurities in there, then it's going to change the molar mass. You know, it's the same thing. Another way that people check the purity of this is quicker, is by checking the melting point. You know, the melting point will give you an indication of how pure it is. If it's like 95% pure, then those 5% impurities screw up the melting point. And that is what happens is the melting point becomes much broader. So it starts to melt at the lower temperature and then finishes melting at a higher temperature. What you want in the melting point is you want a very sharp melting point. And so if you have a sharp melting point, like when it hits this temperature, the whole thing melts, then that's an indication of purity as well. And then you can compare the melting point to what the melting point you expect the pure stuff to be, you know. But anyway, another way is you can check the molar mass here. So here they're checking the molar mass. So 4.08 grams of solid. So we can do it using the way I did it earlier. And that is, we have 4.08 grams of this supposedly pure solid and 3.36 liters, you know. And then what we're going to do is we're just going to do a liter to mole conversion using the molar volume here. And so the molar volume that we're going to calculate is actually, what is 243 plus 273? So I'm just going to do that. 243 plus 273 is 516 Kelvin times 0.08206 divided by 117 torr, and then convert that to atmospheres by multiplying by 760. And so the molar volume is huge because of the very low pressure and the very high temperature. The molar volume is huge. It's 275.0 liters per mole, which is gigantic. And so 275 times 4.08 gives us 1,000. Oh, divided by, I forgot to divide it by 3.36. Divided by 3.36 gives us, this gives us 333.9 grams per mole, which is 334 grams per mole. 334 grams per mole is off. They're expecting 346 grams per mole. 334 grams per mole. Her findings suggested to her that, what her mistake might have been. Does it suggest anything to you? Okay, so she's getting a little lower molar mass. Does it suggest anything to him? Part B is beyond the scope of chapter 14, but you might find inspiration after you have studied chapter 13. What was chapter 13 again? Structure and shape. Structure and shape. Well, there could be a lot of reasons why she's on. Let's see what they said. The difference between, the expected molar mass and the molar mass was found experimentally to be 12. This is the mass of carbon she had. All right. I don't know about this answer, but you can take it for what it's worth. Depends on what the compound is. If you're an organic chemist, you can't just have a carbon, So usually you got to have a carbon and, and a hydrogen, unless it's like triple bonded. If it's triple bonded, maybe, but if it's double bonded, you got to have hydrogens in there. If it's single bonded, you got to have hydrogens in there as well. If it's double bonded, you got to have one hydrogen. If it's single bonded, you have to have two hydrogens. We have names for those units. I erased it, but the difference between propane can be written like this: CH3, CH2, CH3. And so the difference between propane and butane is a CH2 group. A CH2 group is called a methylene. And so if we just keep adding methylene CH2 groups, we can build bigger chains. And we just insert them between the ends. The ends are CH3. And so we could have methylene. Well, methylene is going to be 14 grams per mole because this is 12 from the carbon and 2 from the hydrogen. And so it's actually 12.03 grams per mole difference. And so the mass difference between these two molecules is 12.03 grams per mole, or 12.03 U's per molecule. Okay, so it's a CH2 if it's a hydrocarbon. Now, if you have double bonds in there, it could be a CH, because carbon likes to form, CH2, like there. If you have another double bond in there, it could be a CH. If you have a triple bond, then maybe it's a carbon, you know. But that's for organic chemists. For inorganic chemists, it could be, you know, if you're looking at a buckyball, something like that. So I don't know. It's a little bit odd for me. It's a little bit odd. Just the mass, but it could be, you know, if it were like a 14, it could be methylene. Yeah, then it makes sense. Maybe propane versus butane. Yeah, or CH. But just the carbon, that's the thing, you know, for organic chemists, they work with carbon hydrogen containing compounds. All right. So that's chapter 14. That was all the problems in the homework. Let's look at chapter 15. Here. Next. Chapter 15 deals with gases, liquids, and solids. Well, we just dealt with gases. And so this is going to be more gases, and liquids, and solids. Here's an example of a gas mixture. And so we talk about gas mixtures. This is kind of a poor example of a Dalton's mixture. You know, they're trying to visualize this as a Dalton's mixture. The problem with this is for Dalton's mixture, the volume has to be fixed. The problem with this one is the volume. The volume is not exactly fixed because look at where the mercury level is here versus here versus here. With the changes in mercury level, that's going to change the volume of the gas. And so this is not entirely correct here. This is going to be an error because the volume is changing a little bit, you can see here. And so the volume of the nitrogen is not the exact same as the volume of the O2, which is not the exact same as the volume of the mixture. In Dalton's, the volume has to be fixed. And so here, the volume is about constant, to say. It's about constant. And so that's why they're going to call it 1 liter. Well, 1 liter flask actually holds more than a liter. And so that's a problem. And so this is not exactly, I don't know. They could have made it, you know, they could have made it better. And so what we're doing here is this. Okay, here the nitrogen is usually blue. So let me put that as blue. And so there are a bunch of nitrogen molecules in here, you know, 0.0100 moles worth of nitrogen molecules. So a bunch of nitrogen molecules in here. These nitrogen molecules are going to exert a pressure here. The pressure is 186 millimeters mercury. Okay. Over here, there's oxygen. There's half as much oxygen. So half as much oxygen is going to exert about half the pressure here under the same temperature pressure. So the pressure half as much. But now what we're going to do is we're going to put both the oxygen and the nitrogen in the same container. And so what's that going to do to the pressure? Well, now you have the oxygen colliding with the walls and the nitrogen colliding with the walls. So what we're going to expect is we're going to expect 186 millimeters of pressure from the blue molecules weighing down on the mercury, plus 93 millimeters of pressure from the red molecules weighing down. And so the total pressure here is equal to 186 millimeters of Hg liquid plus 93 millimeters of mercury here. And so 186 plus 93 gives us 279. So it's the cumulative collisions because now both gases are in the same container. And so this is a way of visualizing it in Daltons. The volume doesn't change. The volume is constant. 1 liter is equal to 1 liter, which is equal to 1 liter. And so the pressures have to change here. So Dalton's mixture. And so what Dalton said is that the total pressure, P total, is equal to the sum of the partial pressures, P sub I. Right. I don't know. We'll put that on the bottom maybe. And so it's gas A plus gas B plus however many gases we have in here, plus etc. This is Dalton's. And so Dalton says the pressures are additive. I already went through this. Whereas Avogadro's, this is going to be Avogadro's here. And we're not looking, this is not visualizing it as an Avogadro's. Avogadro says V total is equal to the sum of the partial volumes, etc. And so here we're looking at in terms of Dalton's, because if we looked at this in terms of Avogadro's, then we'd have 1 liter plus 1 liter gives us 2 liters. And the pressure doesn't change. Pressure would be constant. And so in this, this is an aside here. And so Dalton's is important for Avogadro's is good for stoichiometry. When we're dealing with chemical reactions, it's much easier to deal, you know, like the volume to volume conversions in stoichiometry are based on Avogadro's law. Dalton's useful when we do this, you know, like air. This could be like an air-like mixture, or this. You know, this is one of the big applications of Dalton's here, is when we collect gases over water. And so the gas that's being generated here is KClO3 is a solid, and then there's a trace of MnO2, which is the black. KClO3 is white, so the black stuff is a catalyst. Catalysts, what they do is they speed up the reaction. Though sometimes the reaction is a bit slow. They don't actually participate in the reaction in the sense that they're reacting a product. They just basically just help the reaction along. And so we could put it up here, you know, there's a catalyst to speed it up. And in this case, the catalyst is MnO2, manganese 4 oxide. Manganese 4 oxide is found, like geologists know manganese 4 oxide. Geologists know manganese 4 oxide because it's called desert varnish. And desert varnish puts this shiny brown black coating on sandstone rock. It's really hard and a really pretty unreactive coating. And so this is going to form KCl plus 1/2 or 3, not 1/2. How many O2s will form plus O2? 3/2. Excuse me, 3/2 O2 gas. This is solid. So what we're doing is we're generating O2 gas. So there's going to be O2 gas in here, which will color red. So we're collecting O2. This tube, this is a test tube. This tube used to be filled with water, 100%. So what you do is you take a test tube, you fill it to the top with water, you cover it, and then you flip it upside down, and you submerge the open end underwater. And so what happens is this tube was 100% filled with water. And as bubbles of oxygen gas come through here, the oxygen gas rises in the tube and collects at the top, pushing the water level down here. And so the oxygen, makes a convenient way for capturing oxygen gas. You know, we don't want to contaminate it with air. And so that's convenient. So we got oxygen gas. However, it may not be contaminated with the air, but it is contaminated with something else. And the something else that it's contaminated by is contaminated by water vapor. And so what happens is some of this water evaporates and creates humidity. It's a water vapor. Excuse me. When this becomes saturated, saturated equals 100% relative humidity. It might be unsaturated. Unsaturated would be like dry air. You know, dry air is not saturated with water. If you go to an indoor swimming pool or an indoor fountain, you'll notice that the air is a lot more humid. And if it's been equilibrated, then the air has been 100% saturated, meaning it's reached its maximum humidity. And that is the evaporation rate is equal to what we call the condensation rate. And that is the water is evaporating just as fast as it's condensing back in the liquid. Here, we don't like 100% relative humidity because 100% relative humidity is very uncomfortable. We like 20, 30% humidity. 0% humidity is also uncomfortable because the air is too dry. Excuse me. And so, you know, but in a case like this, you know, this is a test tube and the gas is being bubbled. And so one thing is, as the oxygen is being bubbled through the water, the oxygen gas is going to pick up humidity and it's going to get saturated. And so if you were stuck inside this tube, it'd be pretty uncomfortable because it'd just be too humid. But that's it. It doesn't have to be saturated, but given enough time, it will saturate. You know, indoor swimming pools might not saturate because dry air is always being introduced into the room. All right, but the problem is this is a gas mixture. So when we measure the pressure here, you know, the pressure here is P total. Now we did the Charles Law experiment, and the Charles Law experiment acted like a manometer. And so if you recall back to the Charles Law experiment, the weight of the atmosphere here, what's pushing on the outside surface is the pressure of the atmosphere, or the barometric pressure of the barometer. If we get the two water levels equal, take a look, the two water levels are equal. So the weight outside is equal to the weight inside here. If the two water levels are unequal, and so this is the pressure of the wet gas. We call it wet gas, not because it's a liquid. We call it wet gas because it's been saturated with water vapor. And so therefore it's not dry oxygen, it's humid oxygen, which is called wet gas or wet O2. And so the pressure of the wet gas here is the same. You know, if the water levels are unequal, let's say the water level, you know, this is from the Charles Law experiment. If the water level inside were up here and the water level outside were down here, and it's open on the end here. And so what that means is the weight outside is a lot heavier than the weight inside because this is like a seesaw, you know, it's imbalanced. And so this is why we had to push the flask up and down in the water to get the two levels equal. If the water level inside the tube is lower than the water level outside the tube, then the weight outside is less than the weight inside. You know, the pressure inside is much greater. It's being compressed, you know. And so what we have to do is we have to raise and lower the tube until the two water levels are equal. When the two water levels are equal, then we know that the pressure inside the tube is the same as the pressure outside the tube. And therefore the pressure of the wet O2 gas is equal to the pressure of the barometer when the two water levels are equal. All right, but the thing is, that's the pressure of the wet O2. What we want is, we don't want the pressure of the wet O2. I want the pressure of just the pure O2. Okay, so the pressure of the wet O2 is equal to the pressure of the dry O2, or just pure O2, plus the pressure of the water vapor. Water vapor. The pressure of the water vapor. Well, it just so happens the pressure of water vapor just depends on the temperature. You know, the pressure of the water vapor, we look this up in a table. Look up in a table. This, using Avogadro's mixture here would be a pain. You know, it would be a pain. Because you know, the volume, it wouldn't be difficult to figure out. It's just one more step. Using Dalton's is easier here because the volume of wet O2 is equal to the volume of dry O2, which is equal to the volume of the water vapor. And so this makes it easier. We just measure the total volume here, and we calculate the pressure here. Okay, we can't measure the volume of O2 and volume of H2O, you know, here because it's all mixed together. It's hard to figure out. We can calculate it, but we aren't going to be able to measure it. And so it's easier just to measure the total volume and then realize that the oxygen is free to move in that total volume. So it's the same, except the pressure will be, if we get rid of the water vapor, the total pressure will be lower. Here. So the total pressure here is equal to the pressure of the oxygen plus the pressure of the water vapor. Pressure. The total pressure is equal to the barometric pressure, so we can get that. And so we have this. The situation is, why do we have water vapor? Because of evaporation. You know, we got evaporation, water molecules evaporating from the liquid. But at the same time, we have evaporation, which are these up arrows. We also have condensation. So water molecule will come back down and stick onto the surface, this condensation. When we reach 100% relative humidity, 100% relative humidity means that the evaporation rate is equal to the condensation rate, so we've saturated. We aren't going to get any more water. When this is dry, if the gas is dry, then we have net evaporation. But once we saturate this, you know, evaporation and condensation don't stop. It's just reached this equilibrium, what we call an equilibrium, which is the next chapter, in which the amounts don't change. And so this is the equilibrium vapor pressure of water when saturated. Now 100% relative humidity just means it's saturated, but how much, you know, at high temperatures, it's more humid, you know, because you can get more, you know, evaporation. And so at higher temperatures, the humidity is higher. At lower temperatures, the humidity is lower, but all these are 100%. And so at, let's say at 19 degrees C, 19.0 degrees C, it's saturated when it reaches a pressure of 16.5 millimeters mercury. So once we had 16.5 millimeters mercury water vapor in here, pressure, it's saturated. But if we're looking at 30 degrees C, we can put like twice as much water in there, in the air, at 31.8. And so the humidity climbs. So all these are 100%. We can go lower than this, but higher than this, it's not stable, and we'll get some precipitation occurring. And so it just depends on temperature. So we got to figure out what is the temperature. So if the temperature were 19.0, then it's 16.5 millimeters mercury. And so we just take pH2O from the table here and subtract that from the total to get the pressure of the gas. The pressure of the gas is equal to P total minus pH2O. And so this is called collecting gases over water. Collecting gases over water, we subtract out the vapor pressure of water from that. This is from your book here, not from Wikipedia. I think this is from, no, this is not from the book. This is from the lab manual. This is the lab manual. All right, let's take a look at vapor pressure. some more here. What causes some of these to vaporize? What causes some of these to vaporize is just energy, kinetic energy. Not all the water molecules have the exact same kinetic energy. In fact, what we see is a distribution of kinetic energies. You know, the higher the temperature, the more kinetic energy. But that's what we call the average kinetic energy. Now, the average kinetic energy goes up at higher temperatures, but let's say we're at room temperature. So we'll just have this at RT. It'll probably be easiest. So at room temperature, not every single water molecule has the same kinetic energy. Most of them are going to have a kinetic energy around here, most. But there's going to be a small fraction of water molecules that have elevated kinetic energy. And there's going to be a threshold energy. You know, if we go beyond this threshold energy, then they have enough energy to evaporate or vaporize. If we're below the threshold, they don't have enough energy to escape the surface. So all these molecules here, and the bulk of the water molecules, don't have enough energy to escape the surface, but a small fraction does up here. And so this is dry. Let's say this is dry air here. You know, if we have dry air, well, what's going to happen is net evaporation, you know, because this small fraction of water molecules will vaporize off the surface. And so we'll start getting water molecules in the gaseous phase here. And so water molecules will start entering the gaseous phase here. As we get more and more water molecules, then sometimes a water molecule will come and strike the surface. When it strikes the surface, it sticks because of hydrogen bonding interactions. And so it's kind of sticky, so they stick together. But right now, you know, there's more evaporation than condensation. But as we get a higher population of gaseous molecules, then the condensation goes up. The evaporation rate never changes because that depends on this. So the evaporation rate stays the same throughout. What's changing here is the condensation rate. And the reason the condensation rate is growing is because we're getting more and more chances that a water molecule will come and strike the surface and stick. Once we have enough molecules condensing back on the surface, once we have enough here, actually, once we get to this point, you'll notice that here the evaporation rate is increasing. Or actually, no, evaporation rate is not increasing. Evaporation rate stays constant. Evaporation rate just depends on this. And so evaporation rate stays constant. What's increasing is the condensation rate. And so we see, well, obviously the condensation rate's increasing because we're getting more and more molecules sticking. But pretty soon we're going to hit this point where the evaporation rate and the condensation rate are the same. When the evaporation rate and the condensation rate are the same, then we've reached a state of equilibrium. This is a state of dynamic equilibrium. Dynamic equilibrium. Equilibrium means no change, but dynamic means change, you know. And so what it is it's at different levels. The dynamic part refers to the particulate level. And so at the particulate level, evaporation and condensation never stop. That's always happening. But at the macroscopic level, nothing's changing. And so we've reached equilibrium at the macroscopic level because the grams of liquid water don't change and the grams of gaseous water don't change. Here. But at the particulate level, it's constantly going in circles. All the molecules are cycling in circles. Liquid, then gas, then liquid, then gas. But not going anywhere, so it's just going in circles. So we can figure out a room temperature. Room temperature is about 25 here. A room temperature is 30, so 25 is about here. You know, what is the vapor pressure? The vapor pressure of water is very low. You know, it's down here. But they're more volatile things like ethanol. You know, ethanol vaporizes a lot easier. So there's going to be a lot more ethanol vapor at room temperature. And so this is what we call volatile. Ethanol is volatile. Water is less volatile. If we look at diethyl ether is even more volatile. There's going to be a lot more vapor based, on the vapor pressure here, a lot more vapor, diethyl ether. So this is more volatile. And so more volatile. This evaporates easier. There are less volatile things like syrup. That would be less volatile than water. We'd have to blow up the scale here to see it. That's at room temperature. What happens when we change the temperature? When we change the temperature, we're going to change the energy. When we increase the temperature, the whole thing shifts to higher energy. When we decrease the temperature, the whole thing shifts to lower temperature. This is a distribution. It's called the kinetic energy distribution, or kinetic E energy distribution. This distribution has a name. It's the Maxwell-Boltzmann distribution. Well, this temperature thing is pretty interesting because this is not like gases. Normally, when we're dealing with a gas, and a gas looks like this. Oops. The pressure of a gas looks like this. When we look at P versus T, it's linear. This is absolute. This would be Kelvin temperatures. So if we double the temperature, the pressure would double. This is Celsius temperature, so it's a little different, but essentially it's the same. And so it's linear. That's because of, you got to remember pressure is directly proportional to temperature. Oops, K times T, or proportional to T. This is from Boyle's law, something like that. Or was it Boyle's law? Well, there's so many different laws. One of those laws. You don't need to know the names. I don't, actually. And so it's linear. But here you see it's nonlinear. The reason it's nonlinear is because we have liquid in there, and the nonlinear is due to evaporation, because it increases like exponentially. And so we expect gases to increase linearly with temperature, but this is increasing more dramatically. It's like this. And the reason why is the number of gas particles is growing. The number of gas particles is growing because of this. As we go to higher and higher temperatures, we get more and more evaporation. And therefore, we're going to get more and more gas particles. And therefore, the increase in pressure is much more dramatic than if here, the gas particles is not growing. The number of gas particles is fixed. And so here, the moles of gas is increasing. Moles of vapor is increasing. Here. All right, so I guess, is it break time now? Yeah. Okay, we'll go on a break here. We'll start at, let's see, a little after 2. Okay. All right. So let me pause the recording. All right, we'll continue here. We can see how the vapor pressure changes by taking a look at how this curve changes here with temperature. And that's on the next slide. Here. So this vapor pressure, this is called a vapor pressure curve. These are vapor pressure curves. It just shows how the vapor pressure changes with temperature. This is pretty much dictated by the kinetic energy curves here. You can see at T1, if we increase the temperature, the whole thing shifts. The whole population shifts to higher temperature. The population stays the same. And so the area under this curve stays the same. So this is why the height drops here. It just kind of flattens out. But you'll see the higher energy population grows. Higher energy population grows, the curve increases. There's an equation for this curve. It's talked about in Chem 1A. We aren't going to get into the equation. A vapor pressure curve is important. One of the things is this. At 760 millimeters of mercury, the temperature is called the normal boiling point. And so when the vapor pressure equals 760 millimeters of mercury, which is normal atmospheric pressure, then what happens is boiling occurs. And so water boils at 100 degrees C. That is, its vapor pressure climbs up to there. Ethanol boils a little lower. It's more volatile. Diethyl ether boils at even lower. But diethyl ether boils close to room temperature. Excuse me. It's very volatile. And then there's things that are less volatile that have lower vapor pressure. Things that have lower vapor pressure are going to boil at a much higher temperature out here. These are less volatile. These are more volatile over here. It has to do with the intermolecular forces. You know, the intermolecular forces of attraction, what's holding the molecules together is weaker in diethyl ether. You know, these are called dipole. These are H bonds. And water H bonds are stronger, and actually there's just more of them in water than in ethanol. And then you have things with even stronger interactions like sugars. You know, sugars have lots of hydrogen bonding. Lots of hydrogen bonding means they're really sticky molecules, and really sticky molecules are hard to vaporize. And so they're going to be less volatile and have higher boiling points. So the normal boiling point's important here. We can see this here. It's a little, let me see if this works. Excuse me. Oh, that didn't work. I embedded a video on boiling. Maybe it's in the next slide. Here's boiling here. You can see the water of the boil. A liquid, in this case water, boils when its equilibrium vapor pressure equals atmospheric pressure. So the pressure, vapor pressure pushing up is equal to the pressure pushing down of the air. Inside a gas bubble, bubbles of vapor that form within the liquid consist of the same kind of molecules. So we just have a gas bubble there. We have the liquid phase here. Actually, I don't know. You know, the explosion in Lebanon.
As heat.
Oops. Let me see. You can see. I saw the news on that, but you can see really quick what they're thinking. But I don't know if enough information has gone through since it just happened. Yeah, if you're not aware, Lebanon, there was a massive explosion in Lebanon here. Beirut, and unfortunately dozens dead. That's a big explosion. Let's see. This is a video of the explosion. Yeah, there's a lot of debris in there, a lot of dirt and debris in this. You look at the cloud, it's quite, although this cloud is pretty orange here. So that if it's orange like that, yeah, it could be chemical there. Again. Yeah, that looks like it's some kind of storage facility. Oops, let me turn down the volume. There's got to be some kind of chemical explosion. boy, that's a huge shock wave. That's a massive explosion. So initially there's a fire, and then what explosions are typically just out of control, very fast reactions that occur. And so normally they start off slow and then it goes exponential. You know, the speed of the reaction just increases exponentially, and then it gets too fast, causing that explosion. So it starts off mellow at first, but you know, if you have a fire, the best thing to do is get away, because you don't know when it's going to go exponential like that and just go out of control. That was unfortunately got this ad. It's hot, and then boom, it goes. Wow. Oh man, that was like a mushroom cloud there. That looks like a chemical explosion. I mean, the other type of explosion, I mean, pressure explosion obviously is much smaller, and then a nuclear explosion would be a different beast. I mean, there should have been a lot of light, although I don't know. Well, I'm sure I want more information. I was waiting to hear what kind of information they had from that, but that is a nasty explosion. It looks like it was in a storage facility, so it could have been some chemicals stored there. It's like, did you see the downtown LA explosion? That was surprisingly big explosion. Let's see if they had a decent video of that one. You know, this was just paint. I think paint was being stored here. Let's see if they have the video of that. Surprisingly big explosion. So it's hot. It's hot. You got to watch out, because, you know, as things get hotter, they can go exponential. As far as chemical reactions go, the rate of the reaction. Well, that's just a big fire there. Okay, there goes the explosion. This wasn't the best video of the explosion, but there's another video that showed the explosion much more graphic detail. Maybe they have it here. Maybe not. I don't remember where it was. There's a pretty decent video of the explosion, but it's the same thing. When I was working in lab, I had a number of explosions, and in chemistry lab, a lot of reactions. You also have a bucket of ice water. You have a bucket of ice water to cool things down, because you don't want things to get too hot. If they get too hot, then you're risking things going exponential and potentially exploding. And so you have a bucket of ice water, and if things get too hot, you drop it into the ice water to cool it down, or other things. I was doing a reaction that I couldn't use ice water because it was water sensitive. The water itself would react with my reactants. It was sodium metal. I was working with sodium metal and ethanol. I was making sodium ethoxide. And what happened was it's so slow because I had a big chunk of sodium. And the big chunk of sodium, it was reacting so slow, I didn't want to waste so much time. So I started taking my spatula, and this was a big chunk of sodium and ethanol. I started chopping up the sodium into smaller and smaller pieces. And pretty soon I got it into very fine pieces of sodium. But as I got it to very fine pieces of sodium, because it kept breaking it up into smaller and smaller pieces, then the reaction started to take off. And then it started getting hot. And I thought, oh, now this is not good. I need to cool it down because it's getting too hot. And so I had a big, what I did was, as an alternative, I brought a big piece of aluminum metal in there to serve as a heat sink. So I put my reaction, the container on the big aluminum heat sink, but it wasn't enough. And then it happened in the span of like 5 seconds, 5 seconds earlier it was in control, and then 5 seconds later it exploded. So there's a huge, well, it wasn't huge, but there's a big explosion. There's a big explosion in this kind of container. It's called a dry box. So I was working in a box that looked like this. And so my reaction, even the moisture and air was bad for my reaction because my reaction would react with the moisture and air. And so this box was filled with nitrogen. And then I had some desiccant in there to dry out the nitrogen. I couldn't have any humidity. And so the explosion occurred in this box here, fortunately. But when the explosion happened, then a whole bunch of people came running. The box didn't explode, but the box just ballooned out quite a bit. My hands were in there, but there was no broken glass or anything, so it was okay. It was just this pressure shock wave. People came running down the hall to make sure I was still alive or something, but it was okay. But it just happened in a matter of seconds, 1 second everything was all right. There could be firefighters there too. If you're going into firefighting, you got to be aware of that. You're a firefighter there trying to fight that fire in the warehouse, then all of a sudden, and 5 seconds later, it's like that. It's horrendous. You could be a firefighter there trying to put out that fire. It's like a pretty hefty fire there. And then you're met with that. Boy, that is a massive. It must be humid there or something, because of that, the halo that was there on there. Let's see. Unfortunately, 25 kill, 73. I don't know. Likely caused by ammonium nitrate. So you would think, if that was an accident, you would think they'd learn from the China blast. The China blast was ammonium nitrate also. The China blast, and then, Texas City was ammonium nitrate also, So you got ammonium nitrate, but if it was ammonium nitrate, you'd see the thing is, ammonium nitrate should have given you a orange clouds of smoke on the fire. Let's see. Oh, these were, this is not the video. That's aftermath. Ammonium nitrate, remember, okay, the orange smoke. The orange smoke would be clear is because orange smoke like that is nitrogen dioxide, NO2. Or, Nitrogen dioxide gives you the beautiful orange smoke that people look at. So this would be an indication of a nitrate fire. So yeah, it could likely be they were storing, maybe storing ammonium nitrate, and it got too hot and caught on fire. And so if it were ammonium nitrate and you're a firefighter, I don't know if you should, you know, especially if there's a lot of ammonium nitrate, I wouldn't want to be around that. Warehouse. Explosion. The explosion was most likely an accident caused by a fire. Yeah, that's unfortunate. One of the professors at El Caminos from Lebanon, also the stockroom technician as well. So hopefully. Okay. All right, so we're going to switch gears here and go back to chapter 14. No, not chapter 14. We're on chapter 15 here. Okay, so something.
As heat is added to.
Oh, actually, it's working. Turn down the volume. So this is boiling. It's at 20 degrees Celsius.
A beaker of water, the vapor pressure of the water increases, thereby increasing the rate of evaporation. If you
One thing is, do you see where the temperature probe, this is called a thermocouple. The thermocouple is touching the bottom of the beaker. It shouldn't be touching the bottom of the beaker because of thermal gradients. You know, the glass could be hotter. It's just not transferring heat as efficiently. So the thermocouple should be submerged entirely in the water and not touching any glass surfaces.
enough heat is added, the vapor pressure of the water equals the atmospheric pressure. At this point, large bubbles of vapor begin to form in the liquid, and the liquid boils.
Okay, so that was boiling there. And so let's take a look. Boiling point is one of the characteristics. So you could tell, you know, how pure things are by, like, pure water should boil at 100 degrees C. If it's not boiling, let's say it's boiling at 102 degrees C, then it's not pure, you know, if you have water. And so boiling point is used to characterize, you know, pure diethyl ether boils here, pure ethanol boils here, pure water boils here. So that's a property, a physical property of liquids here is the boiling point. What are some other physical characteristics? Well, one is the vapor pressure, you know, that's another characteristic. Here it's capped. So the air trapped in the flask, Erlenmeyer flask here, is going to get saturated with water vapor. And pretty soon this will be 100% humidity. You might not have 100% humidity outside here, but inside here it's going to be 100% humidity if it's been sitting here. If you spill water onto the counter here, it's probably enough. It's probably not enough to saturate the air in the lab because all of it will evaporate and still won't reach 100% relative humidity because the air is fairly dry here. In more humid places, then it's easy, you know, to saturate things. Here, this is what we have, boiling here. This is the energy required. It's not just boiling, but to vaporize. You know, delta H of vaporization is the amount of energy that required to vaporize a mole. So how many kilojoules do you need to vaporize a mole of liquid? Or, you know, it depends on the units. It could be per mole or per gram. You know? And it could be joules, kilojoules, calories, whatever. But whatever it costs you to vaporize, it's the opposite to condense. And so to break these apart costs you a certain amount of energy. Like I used to know delta H of vaporization, 44 kilojoules per mole. And so if it costs you 44 kilojoules per mole to break the water molecules apart to vaporize them, you're going to get that back. And so delta H of vaporization here is plus 44 kilojoules per mole. It's endothermic. It's actually 44.0. So this is plus 44.0 kilojoules per mole for water to vaporize. But you get all that in return if you were to condense all that. So this would be minus 44.0 kilojoules per mole. This is why steam burns are very dangerous, because this is steam, let's say, and if you condense the steam, it releases a lot of energy, and that can cause burns as well. And so minus 44 kilojoules per mole. Or 41, actually here it's 41 kilojoules per mole, heat of vaporization. I don't know why I did. This seems off. But seems off to me. But we'll use it, 41 kilojoules per mole. So it'll be minus 41 kilojoules per mole. This is the heat of vaporization. Heat of vaporization is delta H. Delta H is often called heat, you know, heat. Heat of vaporization, delta H of vaporization. And the normal boiling point of water is 100 degrees C. Some things require a lot of heat, a lot of energy. Mercury, it's not easy to vaporize mercury, 59, and it has a high boiling point. Some things are really easy, like ether. Ether is very volatile, and so it doesn't take nearly as much heat, and the boiling point's a lot lower here. It's going to have a high vapor pressure. High vapor pressure is very volatile, and so vapor pressure, we call PVAP, and delta H of vaporization and the BP are kind of interrelated. You know, the higher the vapor pressure, the more volatile. That means the less energy it takes. That means the lower the boiling point. The lower the vapor pressure, that means not much gets into the vapor state, means the delta H of vaporization is much higher. It means the boiling point's much higher. So this is going to have a low vapor pressure. Honey has a very low vapor pressure. It's very non-volatile. That means its heat of vaporization is going to be high. That means its boiling point is going to be high. Have you tried to boil honey? It's going to be pretty high. And so these are related to intermolecular attractions. You know, the stronger the attractions, the harder it is to vaporize, and the harder it is to boil. Here. This is another property that's dependent on intermolecular attractions. This property is called surface tension. Surface tension. And like here, the reason it's not breaking the surface is because in order to break the surface, you have to break the water molecules apart from each other. Well, they're hydrogen bonding interactions holding the water molecules together. And so they don't want to break apart. This is what causes surface tension. It's the amount of energy required to break the surface. Yes. So you could float, like you could float a paper clip. You've seen, I've done this many times. You could float a paper clip on the surface of water, even though paper clips are made out of steel, and steel should sink. This is not a very good looking paper clip, but steel should sink. But because of the surface tension, you can get it to float, you know. Like this, you know, the water bug should sink. But it doesn't, it floats. It's surface tension. So the higher, the stronger the traction, the higher the surface tension. Let's see. And so the way it's going to go is like this. I'll just summarize this in this way. The stronger the intermolecular forces of attraction, we'll call it IMFs, intermolecular attractions or forces of attraction. The stronger the IMFs, the lower the vapor pressure. The higher the delta H of vaporization, the heat of vaporization, the higher the boiling point, and the higher the surface tension. Surface tension, and there are others, etc. tension. This one here, third one. That's delta H, heat of sub VAP. VAP just stands for vaporization. So delta H of vaporization, or heat of vaporization. That's that one there. It's actually the enthalpy of vaporization. That's what it is. Let's look at intermolecular forces. You know, recently there was a study about lizards. You know, people were wondering, how can lizards climb the wall, or how can lizards hang on to the ceiling? You know, do they have strong claws, or what are they gripping onto? And so somebody studied it, a group of scientists studied it. And so, so they studied it, and they found the secret to how lizards can hang on to nothing, basically glass. And this is the sticky secret of lizards. Tiny hairs on geckos' feet help maximize contact with surfaces, allowing van der Waals forces to go to work. Van der Waals forces are just electrical interactions between these tiny hairs. And so there's just electrical attraction between their feet, the lizard's feet, and the walls. And so this is a long-standing question. Scientists have put to rest the age-old question of how geckos stick to walls. The answer is van der Waals forces, molecular attractions that operate over very small distances. And so they're trying to, obviously they're trying to make this into a technology, wall climbing robots, you know, or design materials that stick to dry surfaces. And so, at least since Aristotle, scientists have wondered how geckos stick to wall. They long ago ruled out hypotheses involving sticky secretions, suction cups, tiny hooks, leaving only two possibilities. One is that the tropical lizards stick to surfaces via a thin film of water. Because water molecules are polar, their electrical charges are unevenly distributed. They might stick to some polar molecule in geckos' feet. Other possibility is that geckos stick because of van der Waals force. This force comes from fluctuations in charge distributions between neighboring molecules, which need to not be polar. Their charge fluctuations naturally fall into sync, creating an attractive force. Semiconductors help decide between the two hypotheses. So biologist Keller Autumn of Lewis and Clark College in Portland, Oregon, and colleagues tested whether geckos could stick to silicon dioxide. Silicon dioxide is quartz, which is polar, and the gallium arsenide, which is not. The lizard's feet were equally sticky on the two surfaces, proving that van der Waals forces at work. That's pretty interesting. Well, anyway, there's been a lot written about this, because this wasn't, I guess this was a while ago, 2002. So what are van der Waals forces? We're going to talk about van der Waals forces. These are van der Waals forces here. So this top picture represents van der Waals forces. These are also called London or dispersion. these. Van der Waals, actually Van der Waals forces are more. We'll just call these London or dispersion. Van der Waals forces can also incorporate these ones, these dipole forces, but they don't incorporate something called hydrogen bonding. And so if we have two nonpolar atoms or molecules, this is time averaged. When we look at, let's just look at hydrogen as an example. Hydrogen has a proton and an electron. Let's say the electron were on the left side. That means this is delta plus over here, and this is delta minus. But on average, this electron is going to move to the other side. And so this is what we call an instantaneous dipole. An instantaneous dipole only happens for one instant of time. That's it. Well, if this is positive on this side, that's going to pull an electron to that side. The electron is going to be attracted to this side because there's a positive over there, right? And so that's going to induce a dipole. So this is called induced dipole. And so here, let's say the right atom, we set up an instantaneous dipole. That is, the electron just moved to this side. And so that's negative over there. Well, that's gonna, if there's an electron over here, it's gonna force the electron to go. You know, electrons don't like electrons in a way because of the charge, negative and negative. And so it forces this electron to travel over here, inducing a dipole. And so on this case, we set up an instantaneous dipole here. Instantaneous. And so the electron just moved over there. This is instantaneous. And then this is induced. It doesn't live very long because pretty soon the electron's going to move again. You know, electron's always moving. So it's going to move again, and this is going to disappear. And so this is a short-lived attraction. But, you know, it's going to break, and then a new one's going to form. And so this continuous breaking and forming new ones leads to a net attraction. And so over time, we get a net attraction between these two atoms or molecules. They could be molecules as well. Like in this case, bromine and iodine. Bromine, Br2, it depends on how many total electrons we have. And so we can look at the periodic table and see how many electrons bromine has and compare it to iodine. All right, when we look at bromine, since I had that, it has 35 electrons here. Iodine has 53 electrons. So 35 and 53. So Br2 is 70 electrons altogether, total. 70 electrons in this. And so when I'm looking at a Br2 molecule is bromine bonded to a bromine like this. There's a nucleus in the center, and altogether there's 70 electrons here, core and valence. Valence electrons, you know, there's only 14 valence, but this is total electrons, core and valence. Let's say all 70 electrons decided to go to the left side of the molecule, then this is going to be hugely polar. If all 70 electrons decide to go to the left side, it's kind of unlikely, but if they did, this would become hugely polar because it got 70 electrons. But iodine's bigger. It's 53, and so I2 is 106 electrons total. And so we have 106 electrons here. Now, if all 70 electrons decide to go to the left side, that's going to be hugely polar. But in the case of iodine, if all 106 electrons decide to go to one side, then that's going to be, you know, significantly more polar than bromine. And therefore, iodine is a solid. It's got stronger attractions because it can set up bigger instantaneous dipoles than bromine. All 106 don't have to go to one side, you know, but iodine, we can set up much larger dipoles, instantaneous dipoles, you know, so much larger delta minus, much larger delta plus. These don't last long, you know, on average is zero dipole than something like bromine, you know, because it's just got a lot more electrons. So iodine is a solid, bromine's a liquid, chlorine's a gas, you know. Chlorine has a lot fewer electrons, so it's not going to generate as big of an instantaneous dipole as chlorine does. And so these are fleeting. You know, in other words, they don't last very long. The number of electrons is a good measure, but sometimes we don't want to count the number of electrons. Sometimes people just want to, you know, look at the molar mass. They look at the molar mass and they can see, you know, which one. And so let's look at a pattern here. If we look at these guys here, these are all tetrahedral, non-polar. Let me see, where am I? Oh, these are all tetrahedral, non-polar, down here. Molecules. The difference is the total number of electrons. Now, the total number of electrons is going to go by, you know, the mass, you know, and so what are we looking here? The temperature, this is the boiling point. Boiling point. So water boils at 100 degrees C. It's water. And so this boils at a higher temperature. It means that tin is less volatile. You know, tin tetrahydride needs more energy to vaporize compared to like methane, silane, germane, stannane, this would be, or silicon tetrahydride, germanium tetrahydride, carbon tetrahydride, or methane. But anyway, tin, why? Because it's not because it's heavier, it's because it's got more electrons. If it's got more electrons, it's what we call more polarizable. This is fewer electrons. And the more polarizable, more electrons, more polarizable means, we can polarize it easier to set up the instantaneous dipoles. And so it's got a higher boiling point, not because it's heavier. Higher boiling point because it's got more electrons, which lets it set up larger instantaneous dipoles than something like methane. Okay, they're all tetrahedral, non-polar, tetrahedral, non-polar. Even if it's polar, let's say water, you know, these are all polar here. Yeah. But this is the most, actually in this series, H2S is more polar. And so H2S is more polar than H2SE because of electronegativity, which is more polar than H2TE. This is the polarity. This is what we call a permanent dipole. And with a permanent dipole, it's a situation like this. And so if we look at bromine chloride has a permanent dipole. That is, chlorine's more electronegative than bromine. chlorine is going to suck the electron density. So the chlorine end is delta minus, the bromine end is delta plus here. This is a permanent dipole, like that. And permanent dipoles are going to be attracted to one another. So the delta minus on this molecule will be attracted to the delta plus on adjacent. And so what we have here is a permanent dipole being attracted to a permanent dipole. It's called dipole-dipole attraction. Dipole-dipole attraction. And so this is the orange things, the dipole-dipole. That's what causes these molecules to stick together here. What causes these molecules to stick together are the van der Waals. But it turns out, or the dispersion, it turns out dispersion forces are present in everything. And so even though this has a permanent dipole, it fluctuates. And so the permanent dipole can grow or shrink depending on where the electrons are in that instant of time. And so permanent dipoles fluctuate over time, but this is the time average one. Over here, these dipoles, these instantaneous dipoles fluctuate over time, but the average one is 0, you know. It's non-polar, so here. And so what we have here is kind of a situation where in terms of polarity, H2S should have the highest boiling point because it has the largest permanent dipole. And so H2S, the reason it has a larger permanent dipole is because sulfur is more electronegative than tellurium. So in terms of polarity, H2S should be the highest boiling point. In terms of dispersion or London forces, H2TE should have the highest boiling point. And so when we look at dispersion, H2TE has more electrons than H2S, and therefore it should be stronger. And so here, when we look at this, dispersion wins out, because if you look at H2TE, it does indeed have a higher boiling point. And so these fluctuations, even though this one's smaller and this one's bigger, the fluctuations are much bigger here. And so an H2TE can fluctuate to very big to very small, whereas H2S doesn't fluctuate as much. You know, because there are fewer electrons, it's not nearly as polarizable as tellurium. So this chart is very confusing, but basically it's this. The more electrons we have, the stronger the dispersion force is, the higher the boiling point. The more electrons we have, the stronger the dispersion, the higher the boiling point. The more electrons we have, the higher the boiling point, because the more electrons means bigger instantaneous dipoles, which means stronger dispersion forces. Okay, and so it looks like dispersion forces are the main part of this curve here, at least this section of the curve. What's happening here? What's happening here is these have roughly the same dispersion, roughly the same dispersion, because they have the same number of electrons, roughly same dispersion. And so the difference is, if the dispersion are the same, then these have permanent dipole. So this is nonpolar, and we see we have increasing polarity here. And so if the dispersion forces are all roughly the same, then the more polar one is going to have a higher boiling point. But otherwise, dispersion is most important here. Now, what's going on with these? These ones have unusually big dipoles. Actually, not that one, these two here. Methane doesn't. Methane follows this trend here. And so, let me erase that. If the dipoles were normal, it should go down, and this should go down, because dispersion should win. And so if the dipoles are normal, then dispersion should win, but these are unusually big dipoles, unusually large dipoles. Well, whenever we have a hydrogen that's bonded to nitrogen, or hydrogen that's bonded to oxygen, or hydrogen that's bonded to fluorine, nitrogen, oxygen, and fluorine, these are the three most electronegative. Three most electronegative elements on the periodic table. That makes unusually big dipoles. These are unusually large dipoles. And then we're going to get unusually large dipole-dipole attractions. Unusually large dipole-dipole attractions. You know, these dipoles are attracted to each other because the positives and negatives that we call hydrogen bonding, H bonding. And so H bonding are unusually large hydrogen, unusually large dipole attractions. And so this would be the H bond here. It's an H bond or hydrogen bond. It's not an actual bond, it's just an attraction. So that's why they're dashed, you know, here. And so between water and methanol, we could have hydrogen bonding occur. Between ammonia and methylene, between water and water, we have hydrogen bonding. Water and ice, this is the ice crystal here. It's being held by hydrogen bonding interactions, these dots here. And so they're connected by hydrogen bonds. These hydrogen bonds are these unusually large ones. And water can hydrogen bond, it gives it a very high boiling point. Ammonia can hydrogen bond, gives it a very high boiling point here. So we can see that. And so these buck the trend here because of the hydrogen bonding, but otherwise the trend goes like this. Dispersion are most important. If the dispersion are the same, then polarity, increasing polarity means higher. And if we have hydrogen bonding, well, that trumps everything else. This is the most important is force. Unless you were dealing with very large molecules. When we're dealing with very large molecules, you know, and so pretty soon, when we're dealing with very large molecules are going to have boiling points higher than 100, you know, because the dispersion forces are huge. And so like asphalt in streets boils at a much, much higher temperature than 100 degrees C because these are gigantic molecules held together by dispersion forces. Asphalt consists of nonpolar hydrocarbons. And so this is pretty confusing for many students, you know, understanding this chart, this graph here. It's not so easy. This is the same graph as in Chem 1A. You'll see it again. All right. Well, liquid water. Well, water in general. This is from the Khan Academy, but water. There's a like biochemistry. If you look at a biochemistry book, chapter 1's water, and so this is probably important to talk about water. You know, there's certain properties of water that are crucial for life. You know, one is water is very polar. So that polarity has. It's an excellent solvent for polar things, you know. Salts, a lot of salts are very polar. They dissolve in the water. Other things. So it's an excellent solvent. Has a high heat capacity. Heat capacity is, you know, how much heat it takes to warm it up. And so water takes a lot of heat to warm up its temperature. We're going to look at heat capacity in this chapter. It has a high heat of vaporization. Well, we already looked at the heat of vaporization. They said 41. I thought it was 44. I'll have to look at it. Water has cohesive and adhesive properties. Cohesion and adhesion. Cohesion is water with water. Adhesion is water with like glass, you know. Water adheres to glass. And so adhesion is water and something else. Cohesion is between the same. Water is less dense than as a solid. So ice floats. Here, common mistakes and misconceptions. Water dissolves everything because it's a universal. That's not true. It doesn't dissolve oil. You know, water dissolves sugars and salts. But there are lots of insoluble salts. You know, the lattice is just too strong. But oil doesn't. All right, that's liquids. Let's go on to, that was gases, and then we did liquids. Now let's do solids. When we look at solids, we're going to classify the solids based on the type of bond that holds the solid together. And so we have ionic solids, and those solids are held together by ionic bonds, like potassium nitrate, sodium chloride, magnesium oxide. We have molecular solids. Molecular solids are molecules, and molecules are going to be held together by IMFs. And so molecular solids are held together by intermolecular forces. Intermolecular forces aren't real bonds. Like hydrogen bonds are like 25 kilojoules per mole to break, whereas the weakest covalent bond is around 100 kilojoules per mole to break. So the hydrogen bonds are still a lot weaker than real bonds. And then we have network solids, network covalent solids, you know, and so let's take a look at what holds these together. So ionic solids has ionic bonds holding it together. Molecular solids have IMFs. And so IMFs, what are they? Well, we have dispersion or London. We have dipole. And we have H bonds. H bonds are the strongest for small molecules. For large molecules, dispersion are going to be the strongest for large molecules. And so that's what holds them together, like I2 solid. Then we have network. These are covalent bonds. Covalent is when we have the sharing of electrons, like quartz and diamond. These are very high. Diamond's very strong lattice. You know. Quartz, also quartz, and then aluminum oxide as well. Another thing that it gives very hard materials, like quartz is very hard to scratch. Same thing with diamond and aluminum oxide. Aluminum oxide in the form of like sapphire. Sapphire is made out of aluminum oxide. It's hard to scratch, so that you have watches that have sapphire glass rather than quartz glass because it's harder. You know, on the Mohs hardness scale, diamonds are 10, aluminum oxide's a 9. Quartz, I forgot what quartz is. Quartz is not as hard as aluminum oxide. I think it's an 8 on the hardness scale. Let's see, hardness of quartz. These are qualitative. They're actual numbers that go with it. But on the Mohs is just a qualitative hardness scale. Mohs hardness. Most geologists have to memorize this. I had it memorized. Let's see. Corundum is aluminum oxide. So diamond's a 10, corundum is 9, quartz is only a 7. I thought quartz was an 8. Corundums are, so sapphire, having a sapphire glass on your watch will prevent it from getting scratched. Unless you scratch it with diamond. Diamond will scratch a sapphire. Sapphire glass. Is it really sapphire? Wow, they're going to test it, maybe. Kind of interesting. Well, anyway, sapphire is pure aluminum oxide. That's what sapphire is. And remember, aluminum oxide's very strong lattice. So it's hard to scratch, hard to react, hard to melt. Can you scratch sapphire glass? Yes. Sapphire is a 9, but if you have a 10, you can scratch it. So sapphire should be scratched by diamond. How easy? No, it's not easy. If you did scratch it, it's not easy to fix. Wow. I wonder what scratched that. It's got to be diamond that scratched that. It is like if you try to scratch that with quartz or sand, sand is mostly quartz. Sand is mostly quartz. And less expensive watches manufactured in mineral glass. So mineral glass is just regular glass. This is what they need to put on phones. You know, if they put aluminum oxide on phones, think how tough. It's hard to break. Well, actually, it's maybe you can still fracture it. But anyway, let's go back to this. So quartz scores a 7 on the hardness scale. Diamond scores a 10. Aluminum oxide scores a 9. But they're all very high melting. It's all actually, this shouldn't be here. Sorry. Quartz is covalently bonded, and diamond is covalently bonded. But aluminum oxide has very strong bonds, but not covalent bonds. Aluminum oxide. I need to move that. Aluminum oxide belongs up here. And so it depends on how strong the ionic bonds are. Like sodium chloride, is it very hard? No, it's easy to scratch. You could scratch this stuff with your fingernail because the bonds are weak. It's only +1 and -1. So it's easy to scratch. Whereas you wouldn't be able to scratch aluminum oxide with your fingernail. That's not going to work. You know, depends on how strong. These are strong bonds here. This is quartz here. Here's quartz. And amethyst is based on quartz as well. All right. Well, okay, it's break time, so we'll take at least a 15-minute. I have to pop out, so it might be a little bit longer than 15 minutes, but check back a little bit. Okay, I'll be back. So break time. Yeah.